Last class, we talked about, I think, emission spectra. We also talked about, so that was looking at like the different colors of lights that were emitted by different elements. We're going to be doing some of that stuff today in lab, which is fun. We also talked about some more mathy stuff like the de Broglie wavelength. So every object, especially electrons, especially small objects, when they're traveling, they have a particle behavior, but they also have a wave component to them when we calculated the wavelength, the de Broglie wavelength for a baseball, as well as some other stuff. We also talked about the Bohr model, and there was this Rydberg equation, which shows us the relationship between different atomic spectra. So 1 over m squared minus 1 over n squared being a term in here. We've got r and 1 over wavelength showing up over here. I'm pointing that out because we'll see something that looks like that hopefully today. Okay, and then skipping around for some reason. The uncertainty principle. So it turns out that the supermicroscopic world, the world of atoms and electrons, is very weird. And so we've talked about how electrons have wave behavior and they also have particle behavior. And so some of that wave nature is when we saw those interference patterns. So if you take two slits, you can see the diffraction of the electron radially from those two slits, and then you create an interference pattern of bright, dark, bright, dark, bright, dark spots across a screen on the back. The particle nature, we're talking about the position, so you can see which slit an electron is going to pass through, because if it's a particle, it can only pass through one slit. And you would be able to see just like individual bright lines through each of the slits. You don't get the diffraction. And it turns out that these two behaviors are complementary properties. So if you know a lot about one, you know less about the other, which feels a little bit confusing perhaps. So if you set up an experiment like this, where you have a laser beam crossing the path of where your electrons are going through, you get no interference pattern, you just get the bright spots where the particles would be traveling through. Basically, like if you shone a light through two slits, you would just see these bright spots. You wouldn't see the diffraction happening, so you don't get the alternating bright, dark, based on the wavelengths of the lights when they're reaching there. Brings us to Heisenberg's uncertainty principle. So the more accurately you know the position of an electron, the less you know about speed. And vice versa. So when it comes to electrons, you can either know where it is, or you can know how fast it's traveling, or you can be uncertain about both, with varying degrees in between. So the delta x is the position, or the uncertainty in the position, and then we've got mv, or mv, delta v, where m is mass, and delta v is the uncertainty in the velocity. And this is bounded by this Planck's constant over 4 pi. So whatever these two values are, they have to multiply to be greater than or equal to Planck's constant over 4 pi. The big takeaway basically that we can't simultaneously know the position and velocity of an electron. You can know one. If you know one with absolute certainty, you know the other one to very low degree of certainty, which is kind of unusual for the world that we're used to living in. So which of these statements best summarizes that uncertainty principle? Both position and velocity can be accurately known at the same instant. Either position or velocity can be accurately known at the same instant. Neither the position or the velocity of the electron can be accurately known at the same instant. There's one of these that it's not. Who knows which one it's not? It's definitely not A, right? We can't know both at the same instant. I think the correct answer here is B. Either position or velocity can be accurately known at the same instant. So we can have high confidence of one, but not high confidence of the other. I believe previously we talked about determinacy versus indeterminacy just a little bit. So classical physics that is like the world that we exist in, particles like baseballs move in a path that's determined by the particle's velocity, its position, and the forces acting on it. So in determinacy, the present situation, the present condition determines the future. So if you see somebody throw a ball at you, and you see that it's coming towards you, you can put your hand up and predict where that ball is going to travel and catch it. That's determinacy. That's what we're used to. However, because we can't know both the position and velocity of the electron, we can't predict the path that it will follow. So you can either, if we're thinking about it as a baseball, you can either see where it is, or you can know which direction it's traveling, but you can't know both to a great extent. So it's sort of like, if any of you have played that backyard baseball game, it's an old game. But there's this pitch that you could throw out that was like a crazy ball, and it's just flying all over the screen. That's sort of how I would imagine it would look like to try to catch a pitch or catch a baseball. So you throw it, and instead of just flying in a nice straight line, it's flying all over the place, kind of like a gnat. So you can see that it's coming generally towards your direction, but you're not sure where it's going to land. And so in indeterminacy, the future can only be described statistically. So we can say most of the time it's going to land in this area, or most of the time the electron's going to be in this area. So location of electrons can be described statistically. And the correlation that I usually use for this, or the analogy that I usually use for this, is if you've got a good friend and you kind of know each other's schedule, you can usually, if you're really good friends, you could probably say with some certainty where they're going to be at a particular time. You might say, oh, my friend Ethan, he's got work right now, so he's probably, over on this side of town, he's probably over at his shift now because it's like in the middle of his shift. And most of the time you'd probably be correct, assuming that he's got a regular schedule, but it's entirely possible that he's got a doctor's appointment that he just didn't tell you about. And so he's not actually where you think he is, even though that was a great guess, right? He's at his doctor's appointment. Versus if you have like a friend that you're not super close with, you can just kind of generally guess, well, I think they have a class right now, so they're probably somewhere on campus. This is sort of what we can do with an electron. We can just kind of make guesses about where the electron is going to be most of the time. And this is just a visual of this concept of trajectory. This is the determinacy thing. So if a baseball player hits a ball, you can watch its trajectory, and the outfielder can go and make a play because they know the way that the ball is flying. They're kind of watching the path and making little adjustments, with wind and spin and other things like that. And the same thing happens for pitches. You can watch a pitch coming in, and assuming it's not going too fast, you could probably make a good attempt at swinging and getting a good hit. With quantum mechanical probability distribution, we're just looking at statistics. So if we've got a very good pitcher and they can pitch it, they can hit strikes, they're reliable, or if we put it into a machine that's always going to shoot them right down the middle, it's not always going to hit right down the middle. Sometimes it'll be outside of that, other times it'll be even further outside of that, but we can just say with some percentage, 70% of the time it's going to be in the strike zone. The other 30% of the time we have no clue where it could be. It could be going the entirely wrong direction even. Okay, so knowing position and knowing velocity. We can either know one or the other with a high degree of certainty. So electron energy is related to velocity, and position are complementary. For an electron with a given amount of energy, the best we can do is describe the electron's position in terms of an orbital. An orbital is a probability distribution that's showing where the electron is likely to be found. Orbitals, there's a bunch of them, but generally I think it's safe to say we can just think of them as shapes. So we're going to be looking at later, we'll be looking at a bunch of different shapes. An orbital describes one of these shapes. So all the orbitals are going to have a specific shape to them. There will be some general categories of shapes. And for any energy value for our electron, that's going to put it into a particular orbit or a particular shape. We're going to just briefly look at some more serious quantum mechanical stuff. We're not going into the details because it's requiring calculus and we don't have that. So Schrödinger has this equation. This is the equation. Schrödinger's equation allows us to calculate the probability. The H and the E here stand for things. And these, I believe it's the Greek letter C, PSI, stands for a wave function. So you can think of throw in something that you would plug into a calculator, like a graphing calculator, and it gives you out a shape. That's what we're plugging in for these wave functions. We're not going to look at what those wave functions are. That's just a symbol that stands in for a wave function. So functions like 1 over x would be a function, or sine of x, right? Stuff that you could plug into a calculator and it would give you out something on a graphing calculator. If you square those, then it represents the orbital. Again, we're touching the very most basic bits of quantum mechanics. So doing a bunch of calculations, it turns out that the size, the shape, the orientation in space of an orbital of our various shapes can be determined by 3 integer terms. Integer meaning that it's like counting numbers, so it's whole numbers 0, 1, 2, 3, 4, 5, etc. Sometimes they're negative. So we're not doing any fractions. So we've got some numbers that are solutions. If we plug them into those wave functions that we're not looking at because they're scary, if we plug them into those wave functions, then it describes a particular shape. And we can add those up, and that tells us the energy of the electron. These integers are called quantum numbers. We have 4 types of quantum number that you need to know. And we've got some rules about what values are allowed. All of the quantum numbers that we know, that we'll need to know, are on this slide. There's 3 big ones. We've got our principal quantum number, n. You can think of, if we can think back to our Bohr model of the electron, we had our nucleus in the middle, and we had these rings around it, right? And these rings represented energy levels, n equals 1, n equals 2, n equals 3, etc. Our principal quantum number, n, is like these energy level shells. Sort of like that. So that's our principal quantum number, n. We've seen n before. That was, again, in the Bohr model. We also have the angular momentum quantum number, which has the symbol L. We also have the magnetic quantum number, m sub L. And then our last quantum number is the spin quantum number, m sub s. So you should know the 4, at the end of the class, at the end of this section, we should know the 4 quantum numbers. This will probably require some memorization. Okay, so our big number, our principal quantum number, this is where we start. This is our first number. This is an integer that determines the overall size and the energy of an orbital. This is like Bohr's energy levels. Right, Bohr's energy levels. We've got 1, that's our lowest energy, 2, more energy, 3, more energy than that. It's any number that's bigger than 1. or equal to 1. So we've got values of 1, 2, 3, 4, and so on. The higher that n number gets, the higher the principal quantum number gets, the further out the shell is, the higher the energy is. It's harder to be out there. It takes a lot of energy to be out there. For hydrogen, we can describe the amount of energy as this E sub n. So this is the energy at a given n value for our principal quantum number. So if we're at 1, then it's got this constant, negative 2.18 times 10 to the minus 18 joules, times 1 over n squared. So at n equals 1, E sub n equals E, or negative 2.18 times 10 to the minus 18 joules. So we'll call that E sub 1. E sub 2, it's going to be that same number, that's a constant. But now this 1 over n squared comes into play. So it would be over 2 squared, and 2 squared is the same as 4. And then the next one, it would be over 9, because that's 3 squared. Then the next one, it would be over 16, because that's 4 squared, and so on and so forth. And the energy sign here is negative, because the electron's energy is lowered by its interaction with the nucleus. So as it gets these higher energy values, when we divide this number by 4, we're getting less energy stabilization, if I'm remembering correctly. Another thing that happens is the energy difference gets smaller. So these layers, I'll call them shells, get closer as n increases, which is also what we saw with the Bohr model. Yeah, so because this is a negative number, when we add a number below this, we're making it closer to 0. We're actually increasing the energy, because it's confusing because we've got the negative decimal and the negative sign. Okay. The net takeaway, though, is that the energy is increasing as we move to these higher values. So 10 to the minus 18 is a bigger number than 10 to the minus 19. If we do this as 10 to the minus 1, but we'd have a negative number in front. Right, so this negative, I'm putting in negative 1. It's not actually negative 1. That's just negative 2.18 times 10 to the minus 18. This is just the negative 2.18. And then the times the 0.01. This 0.01, that's going to be a smaller negative number. It is actually higher energy. And we can see here the energy spacing gets closer as we get to those higher n numbers. It's confusing. It really is. It is confusing. But we can get better at it. Okay. So that's our big shells. Question?
So what is the negative number that represent again?
This is the energy of the electron in a particular energy shell.
Why is it negative?
The electron's energy is lowered by the interaction with the nucleus. So the closer it is to the nucleus, the more that the energy of the electron is stabilized or lowered. Okay, so that's our first one. Our second quantum number is the angular momentum quantum number. which has the symbol L. And L can have integer values from 0 to n minus 1. Practically, this goes from 0 to 3. But it can be limited by our n value. And each value of L is called a particular letter, and that designates the type of shape. We've got different shape groups. So we can have integer values from 0 to n minus 1. So when n equals 1, L equals 0. Because it can go from 0 to n minus 1, and if n equals 1, then L can only be 0, since 1 minus 1 is also 0. If n equals 2, then L can equal 0, because that's our starting value. It can also equal n minus 1, and n is 2, so 2 minus 1, we can also have a value of 1. So we're adding one of these values each time our n increases. And these are our 4 letters. I'd recommend memorizing this table. Our 4 letters are S, P, D, and F. And these specify different shapes. We will see what those shapes look like later. Okay, so if we've got an n value of 3, what values of L can we have? What's our rule for L? What's our possible values? Who remembers? 0, 2, n minus 1. So if n equals 3, plug in a 3 here, and this is 2. So our values would be 0, 1, 2. So our correct answer here is C, and these correlate to the letters S, P, and D. So we can have S shapes, we can have P shapes, we can have D shapes. And again, we're going to see visually what those look like, because I think it's helpful. Then we've also got our magnetic quantum number, m sub L. This one depends on L. L's value. So this determines the orientation of the orbital. So where our angular momentum number, our L, specified the type of shape, this time we're talking about the specific orientation, or we can think of it, once we see the shapes, we're talking about a specific one of the shapes, because there's different numbers of shapes. And our values here range from negative L to positive L, and this includes 0. And again, it's integers, so we're not doing decimals, we're not doing fractions. And the number of m sub L values gives the number of orbitals of a particular shape. So when L equals 2, m sub L goes from negative 2 to positive 2. When L equals 0, m sub L is just 0. Okay, so if we've got L equals 2, what are the values of m sub L that we can have? What's our rule for L and m sub L? M sub L goes from what's the lowest value that we can have for m sub L? For L, it was 0. For m sub L, it's based on L. It's negative L to positive L. I do my L's cursive for this. I'm not sure why. I think that's just how I've seen it. So from negative to positive, and we've got a value of 2. So we've got negative 2, negative 1, 0, positive 1, positive 2 as our values. So our correct answer here would be D. For the numbers part of this, you kind of just have to memorize the rules. Okay, so quick review, right? N is our shell or our energy level if we're thinking about Bohr's model. Inside of that, we've got L. And L, we also often call the subshell. It's the shapes, or shape group, family, whatever you want to call it. And then ab sub L is a particular shape, which we could also call an orbital. And once we look at the shapes, we'll be able to point these out more specifically. But I think this is going to be especially helpful once we've looked at the shapes. I think this is a good way of recapping what the individual quantum numbers mean. And then our last quantum number doesn't depend on any of the other ones. This is our spin quantum number, and the thing that we're talking about for spin is electron spin. So electrons have spin. They all have the same amount of spin. Some of them have positive spin. The values here are positive half or negative 1/2. Electrons have either up spin, they have either up spin, that's the positive 1/2, or down spin, which is the negative 1/2. This one doesn't depend on any of our other quantum numbers, it's separate. So it's only going to ever have values of plus 1/2 or minus 1/2. And the spin is formally called up spin or down spin, which is interesting. Questions so far? All right, describing an orbital. So each combination of our first 3 quantum numbers describes an orbital, one particular shape. So for example, n equals 1, that's our smallest, our lowest energy principal quantum number, or our shell. Our only option for n equals 1 is L equals 0. So L equals 0 is describing the type of shape that we have. Our only option is 0. And then ab sub L, which goes from negative L to positive L, is just going to be 0. And that's describing the one particular type of shape. We've only got one option as well for that one. This describes our 1s orbital. So n equals 1 is the 1 in the 1s. And then our L equals 0 corresponds to the letter S, and so that's where we're getting the S from. And then the m sub L equals 0 is the specific orbital that we're talking about. So we've got principal shell, I was just calling it a shell, or principal level. Those are based on our value of n. If they have the same n and L, then they're in the same sublevel or subshell, so a shell within our particular energy level. Generally, we may notice that the number of sublevels within a level equals n. So this is we're talking about the different values for L, or our subshells. Sublevels is being used interchangeably here with subshells. So if we look at this chart, our principal level, principal quantum number, n, is over here on the left, and then we've got different sublevels. So for n equals 1, that's our lowest energy principal quantum number. Our only value for L is 0. When we go up to 2, our values are 0 and 1, so we've got two possible letter options, S and P. S and P. When we go up to n equals 3, our third shell, we've got S, P, and D represented by the numbers 0, 1, and 2. And within each of these subshells, the number of orbitals, the number of different possible shapes, is 2L plus 1, because it goes from negative L to positive L, and this includes the value 0. And the total number of orbitals in a level is also equal to n squared. So another way that you could see this, for our n values, 1, 2, 3, 4, our subshell values, or our possible subshells, is S, S, P, S, P, D, and then in n equals 4, we also get access to F. So as we're increasing our principal quantum number, so we're increasing the shell, like if we're thinking about our Bohr model, as we're going up these energy levels, we're also adding in another subshell with each time that we go up to 4. All right, we want to list the quantum numbers associated with the 5d orbitals. How many 5d orbitals exist? What does the 5 in 5d mean? The 5 is our n, our principal quantum number, or our energy level, our shell. In the Bohr model, energy level, so it's our 5th rung, or our 5th orbit. D refers to what? Anyone remember? D corresponds to an L value. it's 2. Because this would go from 0, 1, 2, 3. Those are the options. And those correspond to S, P, D, F. So D correlates to 2. So D here is saying that L equals 2. So we've got N equals 5. We've got L equals 2. What are our M sub L values? What are our options for M sub L? These go from negative L to positive L. So our values are negative 2, negative 1, 0, 1, and 2, those being the positive 1 and positive 2. So how many orbitals do we have? How many of these numbers do we have? 5. We have 5 orbitals. And these are all going to have the same designation, N equals 5 and L equals 2. Questions about any of that? A lot of this is kind of just memorize these particular rules and then know how to use them. That's really what a lot of it is. So what are the possible values of N? What are the possible values of L? What are the possible values of M sub L? What are the possible values of M sub S? If you can memorize what all of those 4 things are, you can come up with all sorts of different combinations of quantum numbers. So more practice with these fun rules. Each set of quantum numbers that's listed down below is supposed to specify an orbital. Just generally, quantum numbers do that. Each of these sets contains one quantum number that is not allowed. Please replace the quantum number that is not allowed with one that is allowed. Okay, what is wrong with our first set of numbers? We've got N equals 3, L equals 3, M sub L equals plus 2. One of these is not allowed. Which of these 3 numbers is not allowed? L equals 3 is not allowed. L equals 0, 2, N minus 1. If N is 3, then the maximum value we can have for L is N minus 1. Which is 2.
Then how is C right?
What do you mean, how is C right? C is also, they're all wrong.
Oh.
Each of them has one thing that's wrong. Yeah. So for A, the thing that's wrong is that L can't be equal to 3. Since M sub L is plus 2, we could change L to 2. So if L is 2, then M sub L equals plus 2 is allowed, because M sub L goes from negative L to positive L, and so we've got the positive L value here. For B, our values are N equals 2, L equals 1. So L equals 1 is 1 less than 2. So that's allowed. Then for M sub L, we've got negative 2, and that is not allowed. The reason that's not allowed is that M sub L goes from negative L to positive L. So possible values of M sub L are negative 1, 0, positive 1. Negative 2 is outside of our possible range, so we could change it to any of those 3, negative 1, 0, or positive 1. For C, n equals 1, L equals 1, m sub L equals 0. Again, we can't have L equals 1 for the same reason that we saw above. Goes from 0 to n minus 1, which in this case would also be 0. So L must equal, or must be, 0. And then m sub L is allowed because negative to positive for 0 is just 0. That's our only value. Questions about any of those? All right. So we had looked at atomic spectroscopy before, and we're going to be doing some of that today. So that was where you throw a bunch of energy at an element, and it gets excited, and it produces light. So each of the wavelengths in an atomic spectra corresponds to an electron transition between orbitals, or each band of color in that atomic spectrum, because we were looking at the little flat, wide slides, and they had different little slits of color in them. So those correspond to a transition between orbital values. When an atom absorbs energy, an electron is excited to a higher energy orbital. It jumps up in energy. With the Bohr model, we were talking about it like it jumps maybe from n equals 1 to n equals 3. That's because of the absorbed energy. That excited state, though, is unstable, so it can't stay there forever, and it eventually relaxes to a lower energy orbital. It drops in energy. In order for it to drop in energy, it has to get rid of that energy, and the only way that it can get rid of that energy that we know of is by releasing light. So a photon of light, a little beam of light, is emitted. A little packet of energy that's based on that transition. So depending on the distance, the energy difference in these transitions, that determines the light that's emitted. So if it's a big jump, if it has to lose a lot of energy, then it has to release a lot of energy as light. So it's going to release high energy light, something more towards like the ultraviolet side if it's in the visible spectrum. So violet, blue, purple, somewhere in there. So this is just sort of what I was drawing in the previous slide, but in the Bohr model when I was drawing it. So we've got something that's initially in its ground state. It's in the n equals 1. It absorbs some energy. It jumps up to the n equals 3 level. It sits around for a while. Eventually, it starts to come back down, and so it drops to the n equals 2. And when it does that, it emits some light. And the amount of light that it emits is based on this jump. So this energy difference determines the color or wavelength that is emitted. If we had a bigger jump, a bigger drop, then we would have a higher energy photon that's emitted. If we had a shorter change in energy, it's like if instead of from 3 to 2, if it was from 4 to 3, that would be a shorter jump. So then it would be more towards the red side of visible light. This is sort of just a summary. Again, it's the same stuff that we were saying, so I'm going to skip that. So the wavelengths of the lines that are in the emission spectrum of hydrogen can be predicted if you calculate the difference in energy between any two states. For an electron in energy state n, there are n minus 1 energy states that it can transition to, because it's already in n, so it can't jump to the n value, whatever that is. Like if it's in 2, It can't jump to the 2 because it's already there. So it could jump to the 1, could jump to the 3, to the 4, etc. And so it can generate one fewer line than the energy level that it's in. It could jump one fewer time because it's already in one of those states, so it can't jump to that state. So it's already in one state, so it can't jump there. That's why it's n minus 1. And both the Bohr and quantum mechanical models can predict these very accurately for a one electron system. So if we only have one electron, you can predict these very well. It doesn't work if you have more than one electron, unfortunately. So our energy transitions, we can do some calculations with those. The energy of a photon, this is for hydrogen, equals the difference in energy between the two levels. So our change in energy is going to be our final energy minus our initial energy. So we've got our final energy here. This is that negative 2.18 times 10 to the minus 18 joules that we were looking at previously. And we've got this 1 over n squared term. We've got an f here, f for final. And we're subtracting by the same thing, but with an n sub I, because that's our initial energy. And since they both have the same term up here, the negative 2.18 times 10 to the minus 18 joules, we can combine the two terms. So we combine these parts, and so the 1 over nf squared minus 1 over ni squared get combined. We smoosh them together. And so the change in energy is equal to this constant times the 1 over something squared minus 1 over something squared. And this looks a lot like the Rydberg equation. I think the Rydberg equation was something like this. Wavelength is related to energy, so you could probably do some substitution here. And then m squared and n squared, we're just talking about two different states. So Rydberg was pretty close to right on, just didn't necessarily have all the pieces or all the explanations. Okay. This is a look at different energy levels. So starting with our n equals 1, we jump up to various energy levels, and transitioning down from 5, 4, 3, 2, etc., we get different energy jumps. So our n equals 5 to n equals 2 jump is going to give us 434 nanometers. If we shorten the distance, it goes to a longer wavelength. Longer wavelength means lower energy. So since it's a shorter distance, it's a shorter distance that it's traveling, that's less energy, so it has to be a longer wavelength. And then n equals 3 to n equals 2 gives us the 656 nanometers. We've also got some longer ones and some shorter ones, and those correspond to things that we can't see in the visible spectrum. But this explains our 3 colors of light that we were able to see on the emission spectrum for hydrogen. Okay, so just thinking about our n values, which of these transitions will emit light with the shortest wavelength? So one thing that you'd want to notice with all of these is that the change in n for all of these is equal to 1. So these are all jumping between adjacent energy levels. So there's got to be something that changes when we're thinking about the spacing of our energy levels. Otherwise, they would all be the same. And we're looking for the shortest wavelength. What's a short wavelength going to mean for the light? How does that correlate to something else that we know about light?
Low energy. Oh, high energy.
Short wavelength corresponds to high frequency, which corresponds to high energy. So we're looking for the highest energy jump between adjacent n values. What happens to the spacing of our n values as we go further out? So we think about the Bohr model. I'm drawing these really flat, I don't know why. What happens to our spacing as we increase? Like the n equals 1 to n equals 2, how does that compare to the 2 to 3? What happens to our spacing? Longer wavelength is lower energy, but the spacing between these energy levels gets closer. Spacing decreases. So if we draw it out as like n equals 1, if our n equals 2 is here, then our n equals 3 is going to be smaller of a jump, and n equals 4 will be even smaller. So they're getting closer together the higher our n value gets. So the biggest jump is going to be the lowest between the lowest numbers. So C here is going to be our correct answer. We could also like pseudo quantify this if we're assuming that it's like with hydrogen. We've got this equation, we could put in the numbers and we could actually calculate what the difference in energy is if we wanted to. I don't really want to. Questions about that? For a visual, this is probably accurate spacing. So our n equals 1 is here, 2 is here. This is going to be a big jump, right? This is way bigger than our n equals 3 to 2. 3 to 2 was the one that we chose. The other options were 4 to 3 and 5 to 4. Let me grab these as different colors and then we can put them all together side by side. So we're looking at the distance that is traveled with these energy levels are 3 to 2 is the longest. And those jumps correspond to energy, so that's going to be our highest energy transition. Hopefully that's a little helpful at least. Okay, determine the wavelength of light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. So we're trying to find wavelength going from n equals 2 to n equals 7. We are going to need that equation that looked an awful lot like Rydberg's equation. So delta E equals negative 2.18 times 10 to the negative 18, I think it was, joules, 1 over nf squared minus 1 over ni squared. And lambda equals HC over E H is 6.626 times 10 to the minus 34. C is 3 times 10 to the 8 meters per second. So see if you can get that to work. I think we typically see Planck's constant as joules seconds in this class. Okay, so the place we should be starting here is our n values, n equals 2 and n equals f, get plugged in for our ni and our nf respectively. So we're going to have our change in energy that we calculate first. It's a negative, this constant, joules, and then 1 over 7 squared. Let's do that in green. Minus 1 over 2 squared. So 1 over 49 minus 1 over 4. The value that we get out for our change in energy, 5.005 and some change, times 10 to the negative 19 units of joules. So this number that we get out is the same as our E value for this lambda equals HC over E. So now we just plug in this number of joules for our E, and we should get out a wavelength. So lambda equals our Planck's constant units of joules seconds times our C value with units of meters per second, not joules per second, sorry, joules seconds. So our seconds will cancel, and then we plug in our energy value that we just found. And a bunch of stuff cancels. Our joules cancel, our seconds cancel. We're left with units of meters. And it is 3.97 times 10 to the 7, negative 7 meters. And I accidentally grabbed my 7. Okay. Wrong tool. This would be the same as 397 nanometers. So that's the wavelength of light that hit our hydrogen and gave that energy to the electron to cause it to jump from n equals 2 to n equals 7. Questions about that calculation? I think I've typically given this delta E equation, as well as the lambda equals HC over E and the H and C values on information sheets. So you just need to know how to use them. You don't have to have them all memorized necessarily. Okay, so we looked briefly at this C squared, PSI squared. This is the probability density. It's the probability of finding an electron at a particular point in space. And this is the probability over a unit of volume. Our S orbital is spherical. S is spherical. S corresponds to L equals 0. So L equals 0, that orbital shape, the one orbital that's in there, is spherical. In this spherical orbital, our probability density, the likelihood of finding our electron, decreases as distance from the nucleus increases. More likely to be found close-ish to the nucleus. Which I think sort of makes sense if you have like the nucleus as a point in space, and I were to represent like the electron like a billion miles away. It's really unlikely that the electron for an atom is going to be a billion miles away. It's more likely that it'll be almost right next to it. If we plot out the density, the probability density, this is like if we took pictures every like fraction of a second, we could see where in space that electron is. And it would look something like this. So we've got all these dots, tons and tons of dots here. Each of those dots represents one point in time. And where the electron is at that particular point in time. So you can see generally it's in this vaguely spherical shape. It's hard to see because it's a two-dimensional plot. But for the most part, it's kind of found just right around our nucleus. And if we were to graph this, our radius here on the x-axis and our probability density on the y-axis, the shorter the radius is, the higher the probability density is. A problem with this is that it looks like, based on this plot, it looks like our highest probability of finding the electron is going to be at the nucleus. The electron is not at the nucleus, though, because if the electron fell into the nucleus, all sorts of bad stuff would happen. And we know that doesn't happen because all sorts of bad stuff has not happened, at least in this particular case and instance. There's lots of other bad stuff that happens. It's just not electrons falling into the nucleus. So we've got a different function because the probability density doesn't really paint the whole picture. We've got a radial distribution function. This is the total probability of finding an electron within a thin spherical shell at a distance r from the nucleus. So we basically like take a shell and we put it and we say, what's the likelihood that we find our electron there? And then we take a thin shell that's slightly outside of that. What's the probability of finding the electron there? And one outside of that. And we just kind of slowly paint those shells on, and we calculate the probability at each of those different shells. So this is the probability of finding the electron at a certain distance from the nucleus. Just anywhere around it in a radius from the nucleus. This is our radial distribution function. This gives us a better picture where our electron's likely to be found. And if you take these two values, these two functions, and multiply them together, you get something even better. So this is what the radial distribution function looks like. So we've got a probability of 0 at a distance of 0 from the nucleus. We know that our nucleus is not where the electron is, because the world would explode, or something else would happen that's really bad. It's more likely actually that it's found at 52.9 picometers, a very small distance, which is the same radius that Bohr had predicted, and then that likelihood decreases the further away that you get. So for our 1s orbital, our first orbital, a spherical shape, it's got the highest probability at a distance, and then it decreases as you get further away from that. So the orbits that we saw with Bohr are not entirely inaccurate. It's just that it can be found a little bit inside of that, can be found a little bit outside of that. So where Bohr said the electron is always found at 52.9 picometers, quantum mechanics says the electron is most likely found at 52.9 picometers, but it could be a little outside, it could be a little inside. It's just on average, generally in that 52.9. If we move on to our 2s and 3s orbitals, these are also spherical because s is spherical. This is always the case. Again, this is L equals 0. Because they are n equals 2 and n equals 3, they're larger in size. So you can think of this like we're adding another shell on. Right? N equals 2 is outside our n equals 1, or n equals 3 is outside of that, which sort of goes with our Bohr model where we had counting up different layers. The difference is that for our 2s and our 3s orbitals, we also have at least one node. These nodes are where we have 0% probability of finding the electron there. So like if you're spinning a rope, there's different frequencies that you can spin a rope. That's what we're looking at here. You can spin it so that it's just one nice loop, like jump rope. If you spin it faster than that, to a certain extent, then you can get a node that forms in the middle. If you spin it even faster, then you can get even more nodes, places where that string is not actually leaving that spot. I don't have a string to show you what that would look like. So that's what nodes are. It's where our wave function goes through 0, and when it goes through 0, we have a 0% probability of finding it there. So our 2s and our 3s orbitals, they're still spheres. And then if we do a cutaway, we do a cross section, we can see this white zone in here. That white zone is where we've got no likelihood of finding our electron. So our probability density is 0, our total radial probability is also 0. And our likeliest spot is just outside of that by a little bit. If we go to our n equals 3, we've got now 2 nodes. So there's no chance of finding the electron at either of those zones, and we're most likely to find our electron somewhere out here. So it's sort of like if you've ever had one of those big jawbreakers, where you like lick through the different layers and then there's like colors inside. That's sort of what our s orbitals look like. You lick through a certain amount, oh, a new color. You lick through a certain amount, oh, a new color. That's sort of how our orbitals stack up with each other. Okay, so our s orbitals, and we'll stop after this. Each principal energy level has one s orbital. Since m sub l is always going to be equal to 0, we've only got one s orbital. Our lowest energy orbital in a principal energy state. So for any n number, 1, 2, 3, etc., we're just going to have one. It's always going to be our lowest energy orbital. S for spherical, which works out nicely. And our number of nodes is n, where n is our principal quantum number, minus L. So our 5s orbital, for example, has 4 nodes. So we would have 4 rings in our cutout. Like we saw here, we'd have, instead of 2 or 1, we'd have 4 separate distinct cutout zones where we're not going to find our electron any time. Questions? We'll look at more of the shapes next class.